And okay, let's continue with the second exercise then, which is about the system fundamentals. Same rules as previous. When I looked at the returns, I noticed that 3 of you had returned the exercise and 1 did not yet. Please do it as soon as possible. Time is running, and when I start checking these exercises after the deadline, after that there will be some penalty. I haven't started the going through the exercise yet, so if you feel like you should be returning something, you should do it, say, quite soon. But anyway, so the exercise topic is about the system fundamentals. Last week the exercise was the signal fundamentals or basics of signals. And on the first exercise, actually, there are the first 3 questions about the fundamental properties, where the first one is about linearity of the system, second one is the causality of the system, and third one is the time shift invariance of the system. After that, there is a kind of pen and paper exercise where you basically take a look at this the flow chart, flow diagram, and start following the signal and basically trying to find out what is the output for this form, then determine what are the system parameters A and B, and then on the 6th exercise, calculating the zeros and poles, then determining parameters A and B for this system here, then calculating the zeros and poles again, then generating a sound sample which has some properties like yeah, this is basically the same as the previous exercise. I haven't had any time to check the if you calculate the noise correctly on the first exercise or not. Usually, actually, the German students don't have any trouble of calculating noise if I give you the signal-to-noise ratio in decibels. You still can do paper and pen calculations. Good for you. Keep it that way. And then using the previous signal you generated 9 and take this system and observe how the system modifies the signal. What does it do for the signal? Just by plotting some of the values and okay, it's a lot of signals. Well, plot the signals. On points. Oh, 250 samples. Okay. I see. Yeah, it actually fits. Okay, no worries. So you can plot the signal on the same graph. And okay, so what I'm looking at here is actually the exercise 2 template. All right, so let's go and I will give you some hints how to actually proceed on the first 3 exercises. And for that one, there's a system which behaves like that. It's defined that the output is actually the input plus number 2. But I'm not doing that one. I will show you how to write functions in case you haven't done it already. I already have the my func, but let's see, I will start a new one. Edit, new func. No, not fuck, but new func .m. M files are actually either script files or function files. Does not exist, so we'll create a new one. Okay, good thing about at least the Octave actually gives the function prototype everything that you need. Everything what you need with the copyright there, and actually, well, you can actually use this one as a prototype. I think if you now just click on the help, oops, edit editor, save that one to new func, and then write help on new func. It gives, yes, gives basically the online help starting from here, as long as you basically just define how many inputs or output it has, it understands the form. So practically we can make this one as the input of just X. There, a return value is new func when the input value is X. And just for fun, I will just make a very simple the function where the return value is equal to X plus shift X by 1. So I will shift the data on X by 1 time sample. This is a very rude way of producing a time shift. So I think the shift XX gives the xn minus 1. So this is basically should be formula for yn equals to x of n. Let's make it a little bit more interesting. Minus xn minus 1, n minus 1. So this is a running difference. On the other hand, when you shift it, I think this shift actually does a rotation shift. So the last one becomes the first one. Or was it the first one becomes the last? Yeah, the first element comes, will be moved into the last element. So this is rotation shift. Okay, but now we can use that one. So let's see if I say new func and give it a values 1, 0, 0, 0. Let's see, what does it say? Okay, yep, it works more or less. First value is 1 minus 0. The next one is 0 minus 1. So it's rotating it to right direction. Yeah, okay. Yeah, rotation to right, I think. Okay. So shifting positive way is here the delay. Good. So this is my function, and I would like to now know if the system is linear. Testing for linearity. System is linear if and only if we have, so this is my test vector, and if well, that's not yet my test vector. If the system with the weighted inputs actually produces same as the weighted outputs. So we are talking about this kind of linearity. Sorry, that's the time shift. Where's my linearity? There I have the linearity. Yes, so let's first have a couple of test vectors. X1 and X2. This is a brute force kind of calculation-based method to calculate if a system is linear or not. And there we can actually use any vector. My personal favorite is random values. So 1 times 100 matrix of random values. And by the way, this is not a mathematical proof. It's a engineering proof. Okay, so can I see somewhere where the other tasks have been already handed in? Yeah, there's a small hiccup on that one called GDPR, and I'm not sure if I can. Okay, I will just send message to one which didn't. So personal message to someone who didn't actually return the exercise in few minutes. So, okay, there. Okay, now one of you know that he didn't return to exercise. The rest of you can be actually relax. I have received your exercise, or at least I received a link. Haven't checked if the links work or not, but anyways. So now we have just those vectors x1 and x2. What else we need? A value a and b, and again, value a, well, random number. Haha. Any number. This is not mathematical proof. This is engineering proof. And also the other one, b, random value, as good as any. So yeah, now we can try testing. So basically, let's calculate first this upper part. So we have output y1 equals the equals to y1 equals to, okay, the function was new func with value of a times x1 plus b times x2. So this is the upper part of this flow diagram. We weight the inputs, sum them together, feed it through the system. So this is the first output. Then the second one. Y2 equals 2. We actually first take the system multiplied with A, well, either this way or the other one, then new func x2 times B. So this is the other side of the equation. There. Now we need to check if these are the same. That's the question, and how to calculate it? Well, we calculate the norm of the difference, y1 minus y2. So this is the distance of these vectors, multidimensional vectors. The norm actually is proportional to the distance, and it's not 0. How come it's not 0? It's very small though. Let's see what is the machine epsilon. Meaning, okay, the machine epsilon is 2.2 times e2 minus the 10 to minus 16. So practically this norm is equal to 0. So that norm, that is equal to 0. So in addition to just calculating, you need to do some thinking. That is very, very small compared to these numbers here. So if we are talking about, for example, Earth, which is the diameter is around 10,000 kilometers. So if we have 10,000 kilometers is actually kilometer is point that many kilometers, and we have that portion of that one, it would be in nanometers compared to the Earth radius. I would say it's 0, right? Okay, so we got a linear system. So superposition works. Linear system. There. Practically, when you are having non-zero outputs, they are typically, in this test, they are typically, say, in order of 1 or 0.1. If it's less than or equal to picos, like this one, 2 pico something, then it's same as 0. It's due to the calculation errors. Okay, just for fun. The next one would be testing if the system is causal or not. And again, so causal system is causal if there is no action before reaction. Okay, causality. We can test it by starting a signal. Let me take index, for example, from minus 20 to, or actually 1 to length of x1 minus 1. So I have indexes now. Oops. I wanted to do it not 1 like that, but I want to actually have it minus 20. So now I have a index. I can, for example, stem plot my x1 test vector first. And now I can actually make it to start at some point. I will start it at index 0. So my the third test vector is x3 is x1 dot times double nn greater than equal to 0. So So actually I will be use the U of N to start the signal. All right, so stem X3. Okay. Now we feed in this test vector the system y2 equals new func x3 right there. For example, we can stem that one to see if there, not x2, y2. It seems that okay, but there is actually something before action. This point here. This is an artifact caused by the fact that we actually used the circular buffer to calculate the this output. Remember here, we used shift, which caused actually the value from end to become the first one for the next calculation. Meaning that this is an artifact we created ourselves. It is not part of the real system behavior. So system is also causal since there's only that artifact before the signal starts. The signal started at 0.0 and that one is the artifact. Okay, good. So system is also causal. That's nice. Next. And then we have the time shift invariance. Time shift invariance. Meaning, do we get the same signal in, okay, I have the time shift invariance somewhere. Time shift invariance here. If we feed the signal on the root on the top or root on the bottom. Okay. So let's see, I will calculate y3 and y4 with any of these signals actually. For example, x1 test vector, it does not make any difference. On the previous, the causality, you need to have a 0 initial value to see the effect. And then also see if there is an artifact due to the way the calculations were done. So some engineering is required. Engineering means not only calculation, but also interpreting the values. So time shift invariance. So delay, we have that shift operation again, what we can use for artificial delay. So we have, for example, that y3 equals, we first shift the signal, so it's new func and shift x1. How many time steps? It does not really matter any. I'll just use 3. Again, this is engineering proof. 3 is as good as any other value. Oops. Oh, yeah, of course. 3. There. 3 is as good as any other value. there, and then I'll calculate the y4, which is the shift of new func x1, the same amount of time steps. There. Okay. Now we want to know if these are the same. We can either plot them or we can just calculate. Again, we calculate the norm y3 minus y4. Okay, now we get exactly 0. So system is LTI and causal. Haha. Linear, time shift invariant, and causal. Hint for this 1, 2, 3 exercises. There are 4 different systems, and I think they are quite different. There are nonlinear systems, then there are non-time shift invariant systems, there are non-causal systems also. So you just need to make the math and then interpretation of the calculation results. Okay, let me do something here, since last time I was working on the working with the Octave. It actually crashed. So there we go. Now I have that part already on safe place. So next, let's go to the exercise or part number 3, which is a determine the difference equation for the following system. I might actually do something like that on video camera, just making a system from the flow diagram to show you how it actually works. Okay, example system that I already know the answer. X of n coming in, and then we have, let's make 5th order delay here, multiply by 1/5. Sorry, not that way. 1/5 first, and then 5th order delay, and then we have plus, and then we have multiply -1 and 1st order delay. So comparing the 4-point running average, this has y of n, 4th order running average. That was 4th order minus -1, sorry, or input as minus. So let's do the math here, how to actually make the difference equation. You just follow the signal. This is a little bit messy. Maybe I should redraw it. Well, maybe not. Okay, at this point we have x of n minus, not x of n divided by 5, or multiplied by 1 over 5. Oops, sorry, no camera. There. So, yeah, that was a big mess. X of n multiplied by 1.1 over 5. Delay z2 minus 5 minus to the summing junction, same way as in analog systems. Yn minus 1. That's also minus. Like that. No, plus. Previous value, yeah. The previous value will be actually updated that way, yep. Z2 minus 1, and then we have the system output, and how to actually go through the system diagram. So at that point, now I would like to have different color. At that point, we have 1 over 5 times x of n. Here we have 1 over 5 times x of n minus 5, since there's a fifth order delay. Here we have y of n minus 1, first order delay. That point here we have those subtracted or added together actually. Well, this one minus that one. And at that point, so y of n equals 1 over 5 times x of n. That comes from here, minus 1 over 5 times x of n minus 5 plus yn minus 1. Okay, good. No, this is a paint kind of ink. Okay, good. So we have this one as the system, the difference equation. So let's start from that one. From see big in video. Example, y of n equals 1 divided by 5 times x of n minus 1 divided by 5 times x of n minus 5 plus the previous value. So we are just updating the previous value. So it doesn't show up in here. It shows on the command window though. Okay, so that's our difference equation. That form. How to then calculate the system coefficients. B and A. The B's are the multiplying factors of xn minus k, where the B0 is for this term. So B. So that's the numerator polynomial coefficients or the scaling factors for x, which is input. So that vector, the first parameter is 1 over 5, which is the 0th order delay multiplier. Then we have a minus 1 over 5, but okay, that's for fifth delay. So in between of these, there are the first order delay, second order delay, third order delay, fourth order delay, and then we have the fifth order delay. You need these zeros in between to show that, okay, which are the system parameters for each of these delay. So practically, it means that in here, instead of that, we have this time delay chain. One, two, three, four, and then 5. There, and these parameters, B's, are 0. That one too. 0 gain. Okay. So that's the forward coefficients. Well, that's forward going, so feed forward coefficients. And then we have the AA, which is the y of n minus k coefficients. Let me do it this way. First, we have the y of n. We move this y of n minus 1 into the other side, and then the sign changes. So this is actually the same difference equation, but now it's everything, all y coefficients are on the left and x coefficients are the right. And then we have the AA equals 1 minus 1. You can also add the rest of this, the coefficients, since it's an nth order system in any case. But on the other hand, this tool is also calculating these zeros and poles like they would be on nth order polynomial. But I will do it just for fun, since practically speaking, we are having how many zeros here? 1, 2, 3, 4. So this would be the fifth order polynomial also for the output terms. So tailing zeros. Not required, but it's okay to have an equal amount of parameters for B and A. Okay, so those are the system coefficients, B and A. And here, be careful. 2 of the most common mistakes are done on this exercise. First common error is that you will actually have the this sign error on the feedback term. Another error is that you will swap A and B. This is a common commonly used the habit to have the A multipliers. We call on the system coefficients as with the variable A for the output and the feedback, and B for input terms. Okay, good. So next step is easy. Calculate the zeros and poles and draw zeros and poles on Argon's diagram. Is the system stable? Well, we can actually calculate the zeros and poles like that. Zeros would be roots of polynomial defined by those. Wow, that is easy. So these are system zeros, and they can be anywhere. And as you can see, they're complex numbers. And if I calculate the absolute value of those, okay, they are all on unit circle. Okay, then I can calculate the poles. Roots of polynomial defined by A. So these are system poles. Postelen. Okay, 1, 0, 0, 0, 0. Okay, 1 actually is right on the unit circle. This one here. The rest of those are at origin. But anyways, I think we also have, hey, wait a minute. It's correct. Nobody actually told me about that one. So nobody noticed an error? Sign error. It seems that you can make also a sign error in this one. So feed forward. This term is negative, but it's already negative here. Remember all the signs. There we go. Now we can calculate the system zeros, and we can see that that 1 0 here is actually compensated by that pole, or the other way around. The pole which is not inside of the unit circle is compensated by the 0 which is at the top of it. Yeah, good. And as you saw, it's very easy to make, say, at least critically stable system, since this, with the sign error, actually it would be pole on the unit circle, which means oscillator. Zeroth order oscillator. Okay, which is constant value. So there I have zeros and poles, but it's not on the Argand's diagram yet. Easiest way to calculate the Argand's diagram, which is zero pole plot. Okay, there we go. Haha. So 0 points are on the unit circle, and then there's 1 pole located on the unit circle, but it's also compensated by the the 0, and then the rest of the poles are at origin. Good. This is a stable system. Is the system stable? My system here is stable. Okay, what else? Zeros and poles again. And then the last point would be to calculate the effect. So basically, oops, not that one. Arbitrary signal input. What is the output? Any linear time invariant system. It's called actually filter. How to use filter? Help. filter. Help filter. Whoa. You give it parameters B and A and X, where the A's are the multiplying factors for the scaling factors for output, and B's are the multiplying factors of input. Okay, and they are also the same as in our H of Z. Ha! Great. So we can actually calculate our signal. For example, system output. Now our system as in this example 5-point running average, where we have the BB, feed forward, AA, the tailing zeros are there also, and we can use these system coefficients as a parameters for the filter command to calculate output for any input. I could, for example, use, I will just have the new one here, excess is x1 dot times double n greater than equal to 0. So this is my syst, oops, not x2 but xs. xs, my signal, which starts at origo here, and random values. I then filter this signal with my system 5-point running average system, which should actually reduce the noise. And this is only noise, this signal. So I would guess it looks less noisy, meaning smaller amplitude. So, okay, how to do it? Y of S equals filter BB AA XS. Why I have that funny bracket here? No. Okay, BB AA XS. That's my output. Let me see if I can stem it here with different color. I'm not sure if this one works. Hey, it worked. Ah, yeah. Let's see. Again. X. Hold on the plot. And that's my 5-point running average filtered input. So this is fundamentally how you implement filter in MATLAB or Octave. How to implement it on a real system, there are some tricks there, but you can actually find, if you're using, I think you're using ARM processor on your microprocessor part. For ARM, there is a DSP block, the function set. I don't just recall them, but it's basically provided by ARM, the ARM coalition, and it's a part of this function library, free function library, what you would be using in any case, and one part of the function library is dedicated for digital signal processing. And on the digital signal processing package, actually the those are optimized routines. I don't remember by heart. Does it have a nth order system? The implementation, but I'm sure that it has second order system implementation for very good reason. In embedded system, you always have a cascaded second order system representation on the when you are implementing the system, just because of the calculation errors. A quick what I'm actually talking about here, how come second order systems, what is the big deal about it? Basically, it's about the same as you will be doing the second order systems, cascaded second order systems in these, for example, analog filters on Sallen key analog filter structure. On one gain block, you can actually have 2 poles and zeros. So you can make the second order systems there with a single operational amplifier. For a little bit different reasons, you can do, or it's better to make only second order systems also on the digital systems. But that we will actually revisit later on if we have time. But anyhow, if you have that one big H of Z here, you can actually find the pole pair, complex conjugate pairs that this you can make the break down the system into second order systems. Think of the zero pole diagram. If you have zeros like this, for example, you can pair these and combine those with a couple of poles here. Those. And say, okay, these zero pole pairs are representing one of these systems. Second one would be that one, and the third one usually it's the it might be actually first order system. But anyways, so the on a digital filter or digital system, you get best computing accuracy using second order systems. You can take it for granted for now on. There are very good reasons to do it, but anyways, that's why on the digital signal processing, the function library, you usually have implementations only up to second order systems for infinite impulse response systems. But well, we'll talk about more that next week. What is this infinite impulse response system? Okay, good. I have a feeling that I have actually covered all of the exercise 2 points. Yep. So let's see, where do I have that system is LTI and causal. There we go. I will just copy that part into my history file. And if you have any questions, now it's a good time for me to answer your questions.